Okay, let us get started. Let me welcome you to this 8th lecture of our course on reinforcement learning. And in previous lectures, we discussed rollout at some length, both in methodology and applications, but we always dealt with deterministic problems, no uncertainty, no disturbances. So now we're going to look at rollout and more generally approximation value space for stochastic dynamic programming problems, and also for problems with continuous state and control spaces. So here's the outline. First, rollout for stochastic problems, and we're going to start with one-step look ahead. Then we're going to look at the multi-step look-ahead version, again for stochastic problems. Then we're going to talk about ways to economize on the multi-step look-ahead minimization. And one possibility is going to be certainty equivalence. Another major possibility, which is very popular, and is discussed extensively in the literature, is Monte Carlo Tree Search, which you can view it like pruning, thinning out the look-ahead tree, but a stochastic form of that, which involves limited simulation. Then we're going to talk about problems with infinite state and control spaces, for which rollout and approximation value space, as we have discussed, it does not work because of the infinity of the control space, an infinite number of Q factors to evaluate. So we need to look at different kind of techniques for this type of problems. And incidentally, these are the kind of techniques that are applicable to MPC, model predictive control. Then we're going to look at a special type of problem, which also involves infinite spaces, stochastic programming. It's a very popular model that has been around since the 60s. And it can be viewed as a special case of dynamic programming. And we're going to discuss the special issues associated with it. So rollout for stochastic problems. You remember our favorite figure involving one-step look ahead. At state xk, we minimize overall possible controls, the sum of the current stage cost and the cost to go. However, here, the system involves a stochastic disturbance, WK, and the number here within the braces is a random variable. So in order to minimize over numbers, for this to be a well-defined minimization, we have to take expected value. The expected value of this, in other words, the weighted sum of these random values weighted with the corresponding probabilities of WK. So here I'm showing also, in general, the cost function approximation is some J tilde. However, here I'm going to focus on the case where the cost function approximation is obtained by running some policy, pi, which we call the base policy. So this jk plus 1 pi is the cost function of some given policy, pi, starting at time k plus 1 from this next state. Okay, so this is similar to what we had before, but before we had a slightly more general situation where we were running some kind of heuristic. Now we insist that this heuristic is not arbitrary, but it's rather a policy. It's a policy pi. In other words, a rule that tells us what action to select at every possible state and time. So this is the minimization for the case where we have rollout with this pi-based policy. We minimize at state xk overall u, and we obtain the rollout control. Now, the minimizing control is the one-step look-ahead policy. And of course, we want this to be good and perform well. So pi, we're going to be calling it base policy, and pi tilde, the policy that implements these minimizing controls, is going to be called the rollout policy. And there's an important fact here. There's a cost improvement property that says that for every state xk and every k, the rollout policy performs at least as well and usually better than the base policy. Now, we dealt with cost improvement in the context of deterministic problems also, but we imposed various conditions like sequential consistency, sequential improvement, and so on. It was not automatic that cost improvement holds in deterministic problems, basically because these base heuristics could be anything. They could be as stupid as they get, okay? They can be anything at all, and they had to have some basic property so that they did not do crazy things, and we could get an improvement. And we impose the assumption of sequential improvement, sequential consistency. We don't need these assumptions here because with this choice of the base policy as being a legitimate policy, we automatically get sequential consistency. So it holds because pi is a legitimate policy. It has a sequential consistency property. In other words, for visiting the same state at the same time, it will do the same thing. Okay, that's regardless of how it got there. That's a property of any policy. It's defined only by the current state and time, the action that you use at any state and time. So we're going to prove actually this cost improvement property. However, let's first talk about some of the difficulties associated with the stochastic rollout. The big difficulty is lots and lots of expected value calculations. If you're very, very lucky, this expected value may be calculable in closed form. However, usually you're left with no option other than to calculate this expected value by simulation. This means running lots and lots of samples of WKs and averaging them by Monte Carlo, okay? So there are many, many different sampling possibilities here because W can take different values and also U takes different values. So there's a lot of simulation involved here. And moreover, to calculate this quantity by simulation, you have to run the base policy to the end of the horizon, right? Lots of steps to simulate, lots of variance involved, lots of Monte Carlo samples needed. So how do we deal with this, this central problem of the simulation effort? There are various ways that we can try to approximate this base policy cost. One possibility is truncated rollout. In other words, we don't simulate this expression all the way to the end, but rather up to some limited number of steps. There are also other possibilities. Prune the look-ahead tree, okay? Prune some controls and therefore not simulate them, or at least not simulating them very fully. Another possibility is a certainty equivalence approximation. Yes, we take this first expected value and we calculate by simulation, but for the remainder, we plug in for the remainder that involves uncertainty from time k plus 1 to the end, we make a certainty equivalence approximation. And we treat this, we calculate this as a deterministic quantity. That has a very, very radical, that can affect a very radical reduction in simulation effort. And we will see that because of our framework based on Newton's method, we can be assured that the loss of performance is not going to be too large. So certainty equivalence is a major way to cut down on the simulation, and we're going to discuss that in this lecture later. Then use limited simulation. In other words, cut down on the Monte Carlo. Instead of doing 1,000 samples of Monte Carlo simulation, if a control does not look very promising, we just simulate a little bit just to check it out, like 10 samples instead of 1,000. This leads to a method called Monte Carlo Tree Search and related methods, and we're going to discuss it also in this lecture. So to summarize, we have stochastic rollout, more generally stochastic approximation in value space. The big problem is the amount of simulation we have to do these calculations. And there are a number of remedies which we're going to discuss, which work more or less depending on the problem at hand. Some questions? Okay, so before we go into these issues, let's discuss an application. One of the very first applications of stochastic rollout, perhaps even the first. I mentioned this application in the context of backgammon, Tesoro's program in 1996 and his earlier programs. Rollout was applied in game context before Tesoro, actually, but Tesoro did the first really challenging study and an in-depth study of all the ramifications of simulation, truncated rollout, and so on. So let me remind you about backgammon. It's an old game of strategy and chance because it involves the roll of a die. And at the typical step, you have a board position, and there are white pieces and black pieces, and they move according to certain rules, and the possible moves at any board position are controlled by the roll of a die, okay? The die is like, okay, 3 and 5 means one piece can go can move 3 steps, another piece can move 5 steps. So the board positions that can result after this position here are random and depend on the roll of a die. But there are a number of positions here. And in the case of backgammon, they're in the order of 20, 30, 40, somewhere in that range. So the look-ahead tree here is fairly substantial in terms of its breadth. In terms of dynamic programming, the states here are the board position, but also the dice roll, okay? Because that's what we know when we make the decision of how to play the roll. So that's the state. And of course, there are zillions and zillions of states, okay, an astronomical number. Given now the current state, the board position, the dice roll, the actions that we can choose are the different ways of playing the dice roll. And they're defined by these possible next positions. And the stochastic disturbance is the dice roll. So from this, we move to those, and then we roll the die, and then we have to play again. So that's where the stochastic disturbance comes in. Okay, so I think I mentioned the history of this. There was, around 1990, Tesoro developed this TD Gammon program, which involved one-step or two-step look ahead with cost function approximation, but without rollout. This was called TD Gammon. And the cost function approximation was trained with a form of approximate policy iteration that used TD lambda, a temporal differences algorithm. You don't hear much about TD lambda these days because other methods have become more popular. But in those days, it was a novelty and a very central focal point of reinforcement learning. So Tesoro applied this temporal difference algorithm, and was the first application that was really on a very challenging problem. And somehow it worked. It trained for a long time. I understand months, okay? We're talking about 1990. Computers were very primitive at that time. So Tesoro had his TD lambda work for lots and lots of time and provided a cost function approximation. That cost function approximation was bootstrapped on a one-step look-ahead scheme, and it produced TD Gammon, a program that could play online. Now that program played pretty well, came close to beating the world champion, certainly was beating all the backgammon programs that were available at that time. There were programs based on so-called supervised learning. In fact, Tesoro had written one, but other people had also written programs like that. But this TD Gammon beat decisively all of those. It came close to beating the world champion. Now, TD Gammon did not involve this rollout, and Tesoro introduced in 1996 a truncated rollout scheme, whereby the cost function approximation that was used at this step was obtained by running TD Gammon for a number of steps forward and taking the TD Gammon approximation cost at the very end. So it was a truncated rollout program, and it played very well, much better than the one without rollout. Rollout was the decisive difference, and it was playing better than any human, as well as much better than all the previous programs. And I think we've talked enough about rollout to understand the reasons for that. There's a better Newton step and so on. However, it's really amazing to contemplate how Tesoro managed to do that, because we're talking about 1996 and computers were very primitive. So imagine generating training samples by running games all the way from here, all the way to the end. So from this position here, run 1,000 games, okay? And average the results. What percentage black won, what percentage black lost. Do this for all the 30 positions. Do this at every game, okay? And the amount of simulation was overwhelming. Hence, he had to introduce truncation. And also, he had to use parallel computation. One nice thing about Rollout is that it's very well suited for parallel computation. Why? Because the average scores here can be done in parallel from every one of these positions. So if you have 30 positions and you have 30 processors, parallel processors, you can do this in parallel. But not only that, Monte Carlo simulation is very well suited to parallel computation, right? You can generate samples in parallel. So if you have here, let's say, if you have 30,000 processors, you can probably use them to generate, to speed up the computation. In Tesoro's time, this required a lot of online computation, and generally it was thought that Rollout is just too slow for online play. However, now if you look at the internet, you will not find a Rollout program in the internet. You'll find a lot of TD Gammon lookalikes, and they play a pretty good game, but stochastic Rollout is not available in the internet because it just is too slow. That's the major difficulty. And people in the world of backgammon think of Rollout as being optimal, the optimal policy. It's not optimal. We know that, right? It's not optimal, but it plays so well that they think it's optimal. And it is the yardstick against which the quality of all other programs are measured. So that's the story of TD Gammon, and a lot of the concerns that arose at that time are still concerns today. The issue of simulation and the amount of it and how you overcome the excessive simulation problem is central still. Any questions here? You guys take a lot of things for granted, but in those days, in the 90s, this was really an eye-popping success. It's like AlphaZero, but better than AlphaZero. And I think I may have mentioned earlier, it got me into this field because I just couldn't believe my eyes that dynamic programming could be used in such an approximate mode to address problems that were completely beyond the horizon of possibility at that time. A lot of computer scientists are fearless, okay? I would be totally scared of addressing a problem like backgammon. Computer scientists just go right in. And sometimes they succeed, sometimes they fail, but then when they succeed, it can be really impressive. So now let's turn to theory. The cost improvement property for the non-truncated version of rollout. If there's truncation, you can't prove cost improvement. You can prove that there's a Newton step involved and so on, but you cannot prove cost improvement. So let's look at the non-truncated version of rollout and let's prove this property. Okay, let me remind you the notation here. Pi is the base policy. Pi tilde is the rollout policy. And we want to prove that for every state and every time from 0 to capital N, this property holds. And the way to prove this is by induction. The proof is very simple. It's just one line, okay? One equation, one string of equations. So we use induction. Clearly, this relation holds for k equals n because it reduces to the terminal cost for rollout and for base policy. Base policy is g sub n, the cost function, the terminal cost function. So let's assume that this relation holds for k plus 1, and we're going to prove it for k and for every xk. So here's how we go. We express the cost to go for the rollout policy starting at state xk as so. Now, what is this equation? This first equation is just the dynamic programming equation for pi tilde, right? The cost at xk of pi tilde is the expected value of the kth stage using mu tilde k, pi tilde, plus the cost to go of the remaining stages using pi tilde starting from the next state, and expected value of that. That's dynamic programming, but focused on pi tilde only, right? Okay, now we upper bound this by this expression here, where we use the induction hypothesis. This thing here, cost to go of the base policy, is by hypothesis, by the induction hypothesis, larger than the cost of the rollout policy. Okay, so we have this inequality. This holds for every possible value of the inside the parentheses, so it holds. That's what I'm saying here, that the first inequality goes by the induction hypothesis. Let's go to this step here. The second equality holds by the definition of the rollout algorithm, right? What is mu tilde k of xk? It is the minimizing u in this expression, right? By definition. That's what rollout is. That's how it's defined. So this is equal here. And the minimum is smaller than what you would get for any other control, including the one of the base policy. Mu case of xk is the control applied by the base policy. And the rollout policy minimizes in this expression. So this is greater than that. And by the dynamic programming equation, this is equal to the cost to go from time k at state xk of the base policy. So we assume that this is less than that, and we prove that this is less than that as required by induction. And that's the proof. It's not difficult. And by the way, this is the proof that you would use for a deterministic problem under the sequential consistency assumption. It's exactly the same steps without the expectation, without the expected value. The proof for under sequential improvement, which we did actually in class, is different, does not use this argument. But the proof under sequential consistency uses exactly this argument, but simplified because it's a deterministic problem rather than a stochastic problem. Okay. Just wanted to make sure that we do some theory here. I'm a theoretician, as you know, right? Questions? Okay, so now let's go to implementation issues of stochastic rollout, assuming a finite control space, right? Because we want to choose between a finite number of alternatives, and in particular, given the current state xk, for every control uk, we compute this expression for that control, and this is the Q factor associated with the pair xk and uk, but corresponding to the policy pi, because we're going to take as cost to go that policy over here. And then we minimize over uk. So we have to compute for every u the corresponding Q factor and select the u that has the minimal Q factor. Now, another way to do it also is to calculate Q factor differences between controls and then find the one that has, for which the Q factor difference is positive for every other Q factor, right? Now, the way we're going to calculate, of course, the expected value is by running for every u, run this random sequence of w's many, many times, many samples, all the way to the end. And then we average these samples by taking the sum and dividing by the number. And then we obtain the Q factor, or an approximation to the Q factor, through their average cost. Because we average over a finite number of samples, there's going to be some error, right? We're going to get an estimate of this Q factor, and there's going to be some error, some random error, the error of simulation. So that's what I'm saying here. The number of samples is finite by necessity, so the calculated values, Q hat, are an estimate of this Q. They are approximate, and they involve some stochastic variance. There's an error variance. There's an error, and there's a variance associated with that error. And of course, the more samples we get, the smaller error we have, and usually we estimate the variance of the error through the central limit theorem. Now, in Monte Carlo simulation, there's a major theoretical subject. How do you do variance reduction? How do you organize the sampling that you do so that the simulation error that you get has as small variance as possible? If you do your simulation in an improper way, then you may get a lot of variance error, but people in simulation have studied a lot the way to organize the samples so that you get a small error as possible. And what we would like to do actually is to reduce the variance of the Q factor differences, because that's what is the thing that can play a role. And now notice that if you're differencing two random variables, and depending on the probability distributions here, the difference may have smaller or larger variance. Generally speaking, doing Monte Carlo on the difference of two random variables is a tricky subject. okay? Because the errors in the samples may be aligned or not aligned, and that can make a big difference. And there's a section in your textbook that argues that it is often best to use the same sample disturbance trajectories for all UK. In other words, let's say there are you have two controls. Simulate the first control using a set of samples, and then simulate the second control using another set of samples. Now, your book argues that it is better to choose the same random samples for both, okay? It's the same W sequence, the same random seed, if you'd like. And okay, to understand this, you need to go into the probabilistic arguments, but there's a simple example that illustrates this. Okay, let's forget about this complicated setting. Let's try to, suppose you have two numbers, Q1 and Q2, and you want to calculate their differences by simulation. So you take a sample of the first one. This is the sample of the first one. It involves a W1, okay? That's the error. Take a sample of Q2. It involves this error W2. Now, if you take the difference between these two and look at the variance of S1 minus S2, then a simple probabilistic argument where you calculate the variance of this shows that the variance goes down as the correlation of W1 and W2 increases. In other words, the better correlated W1 and W2 are, the smaller the variance of the difference is. In particular, suppose that W1 and W2 are perfectly aligned and the errors are exactly equal. In other words, you use the same random seed to generate W1 with the random seed that you use to generate W2. Then W1 is going to be equal to W2, and the difference, S1 minus S2, is going to be exactly Q1 minus Q2. And it's going to involve no variance at all, zero variance. Okay. So this is true for this example, but something similar happens for the more complicated case here. People sort of ignore this subject. It sort of goes unnoticed, but in fact, it can be very important in practice, in simulation, in general, but also particularly in the case of reinforcement learning. Any questions here?
Why we should use the variance of two factor differences and not just each of the two factors. Each of the two factors is random variable. Why are we reducing the variance of two factor differences?
Okay, these you're going to calculate separately, okay? But then to find the minimal Q factor, you have to look at the differences between the two, between all the possible differences. Okay, that's how you're going to declare the winner, by looking at the differences. The absolute values don't matter. You can add the same number to all of them. You can add 1,000 to all of them, and then the minimum is not going to change. It's the differences that are important. Yeah, in terms of how you're going to organize your software, of course, you're going to calculate all of those and find the one that's minimum. On the other hand, so you're not going to bother with the differences, but in terms of the performance of your scheme, or whether it's going to give you the actual minimum or it's going to give you something else, depends on the variance of these differences, because one can overtake the other, and it depends on the difference between the two. The error of the differences that makes is a critical factor here. Okay. So now let's go to multi-step look ahead, rollout for stochastic problems. You remember our figures for multi-step look ahead approximation in value space. It involves at a given state xk, a dynamic programming minimization over L steps. And then the future is approximated by some J tilde, which in the case of rollout is taken to be the cost function of the cost function value of the base policy at the state L steps ahead, okay? So now this is a substantial minimization that we have to do by dynamic programming, and it involves finding a policy here, not a sequence of controls, a policy, because this is a stochastic problem. The first element in this policy is going to be just the single control that you apply at xk, it's uk, and the remainder is going to be some mu functions. Then once you solve this problem, you select as your rollout control, the control that you apply, this first component, and you throw away the rest, and this defines the rollout policy. This u tilde k you apply at state xk. Generally speaking, we take it as given that the longer the look ahead, the better performance of the rollout policy. This is not always true, but it's true in practice, okay? There are theoretical facts that are not true in theory, but they are true in practice. You can find counterexamples, artificial counterexamples, where by increasing the look ahead, you get a worse policy. But these examples are artificial, and they are not representative of the practical world. In practice, the more look ahead you have, the better your policy is going to work. With probability 1. On the other hand, so we want to have long look ahead, but the problem is that the necessary simulation increases very rapidly with the length of the look ahead. Look what the problems that are involved here. First of all, to simulate the rollout policy, we have to search over a much larger number of next states. Is the next state L steps ahead, not one step ahead, but L steps ahead. So the number of simulations of the future cost increases exponentially with the length of the look ahead. Similarly, the number of these terms also increases exponentially with the length of look ahead. And you have to calculate the expected value of that. Again, you need to do a lot more simulation. So the simulation here can be overwhelming, and you definitely have to do something about it in most cases. So that's the big issue. How do we save in simulation effort? Okay, truncated rollout suggests itself, right? Where is truncated rollout going to help? It's going to reduce the amount of calculation needed for this. Instead of doing a simulation all the way to the end, we're going to do a simulation only for a few steps forward. That's going to cut down the amount of simulation by because it increases exponentially, okay? So that can make a big difference. Truncated rollout can make a big difference. The second simulation saving approach is to use certainty equivalence. Here we have a disturbance sequence that affects this calculation that starts at WK, goes to WK plus 1, WK plus 2, all the way to WN minus 1, all the way to the end. So what we do is we allow WK to be stochastic and take the expectation with respect to that, but fix the subsequent values, WK plus 1 to WN minus 1 to some deterministic values, some nominal values. Now that cuts tremendously on the simulation. Deterministic simulation is much cheaper than stochastic simulation. And the main thing And this is why I insisted to give you the insights associated with Newton's method. This is still a Newton step. Even after you do the certainty equivalence approximation, this is still a Newton step that maps performance, that maps J tilde to the cost function of the rollout policy. And in practice, this works quite well, almost as well in many cases as the long simulation that does not use certainty equivalence approximation. It's a big time-saving possibility that at least one needs to try. There are also some intermediate, some approximations to the certainty equivalence approximation, whereby instead of fixing the W's to some nominal values, you allow them to take one or two values, okay? Like two values. That's going to be a limited simulation as opposed to a full-blown simulation with a reduced number of possible values of W. But we're not going to focus on that very much. We'll just look at the certainty equivalence approximation as being the limiting case, which is also you can reason about it in a more intuitive way. So we have truncated rollout, certainty equivalence approximation to cut down the simulation. And the third one is Monte Carlo Tree Search. Monte Carlo Tree Search is basically a form of limited simulation. And the idea is that some of these controls may be really bad. And after a few simulation samples, you can tell that they're not doing good things. Well, it's not worth then spending a lot of simulation effort for these not very promising controls. That's the idea of Monte Carlo Tree Search. Focus the simulation on the most promising controls and treat the other controls lightly. Just check them out to make sure that you have not overlook them completely. Okay, so there's not much we can say about truncated rollout, but we haven't said so already. And what we're going to do is focus on certainty equivalence and also on Monte Carlo Tree Search. And as I mentioned, certainty equivalence maintains the Newton step character, but Monte Carlo Tree Search does not. It does not give you, it can, sometimes it will work very well, but some other times it will not work well at all. Whereas the other one, certainty equivalence, typically works reasonably well. Okay, so let's go now to certainty equivalence approximation, and we're going to sort of look a little bit more closely on why it requires much less simulation. Remember, we're looking at multi-step look ahead at the current state. And instead of xk, I call it x0, okay? Let's focus on, let's translate everything to 0. So this is the current state. And without the certainty equivalence approximation, multi-step look ahead is going to work as follows. We look at all possible U0s, all possible controls, and there are 2 in this figure here. Then this is followed by the generation of the disturbance, WK. So these are going to be the next states, X1, all the possible next states. They're in layer 1. Then we apply U1, and we generate more possibilities. And from there also we select W1, and these are the next states 2 steps ahead, X2 at layer 2, and so on. So for L steps, we're going to get to this layer L. And the number of possible next states is what you see here. It grows exponentially with the number of the number of look-ahead steps, right? But there's also a 2-stage expansion of the number of next states with every layer. Okay, so now we've generated all those. We have to do stochastic rollout after that, right? So we have to go from k plus L all the way to N. And that requires also an exponential number of exponential amount of simulation because of the fact that we have to do Monte Carlo simulation, and the number of disturbances for each one of those grows exponentially with the size of the horizon from layer L to the end. So this is all the work that we have to do without the certainty equivalence approximation. Multi-step look ahead, look at all the next states, simulate them all the way to the end, get numbers, and then do dynamic programming over this tree. Okay? So now let's look at the certainty equivalence approximation. So what we do is we fix these W's to some nominal values and then do the same thing. So from the current state, we allow the first disturbance to be stochastic. And then we take the controls after that. These are the next states, one step ahead. However, here we fix WK plus 1. So we only have to look at the controls available at these states. So we got into layer 2, but the expansion is less of the tree. And we go down, and instead of expanding by 2 steps, U and W, we expand by only 1 step. As a result, the expansion factor of this tree is much smaller. And if you want to get to the same number of next states, you have to go further in look ahead. Essentially, you can get the same number of states with twice as much look ahead. And now from each one of those, you have to do deterministic rollout, which is much cheaper than the stochastic rollout. So here's the twofold benefit of the certainty equivalence approximation. We do deterministic rather than stochastic simulation from the terminal states of the look-ahead tree. And moreover, there are fewer applications of the base policy because, fewer applications of the base policy because there are fewer number of states at the base of the tree. And because we have to do less simulation, we can afford to look further down, look twice as long into the future, which improves performance for a given computational budget. So that's the idea: increase the amount of look ahead with the same computational budget. And this certainty equivalence approximation allows you to do that. And that's the main benefit, less simulation. It's also very easy to apply in practice. There's no complicated software associated with, no complicated programming associated with the implementation. First step stochastic, all the remainder deterministic. Of course, a question here is, how do you pick these nominal values? And that's where insight into your problem may be important. And like I said, also another possibility is to do a limited simulation with 2 nominal values or 3 nominal values that are sort of representative. There's a lot of art that goes into here to make a method succeed, but long look ahead is very important in these problems. Questions? Yeah.
The second benefit, there's like fewer applications of the base policy, and then viewed from the perspective, there's no code stuff anymore, so there's fewer applications.
No, it is fewer applications because for the same amount of look ahead, the number of terminal states is going to be much less. So these applications of the base policy from here onward, base policy is applied after we reach the last layer. So for the same L, let's say L equals 10, you're going to have the number of states ahead is going to be much smaller, exponentially smaller. There is also an advantage, an extra advantage, because deterministic simulation costs less than stochastic simulation. So even from the same state, to do a simulation forward, it's much more expensive here because the simulation is stochastic than it is here because the W's are fixed.
Okay, so if we want to take the advantage of the like longer look at then the fewer applications will be like this and more than 6 years.
Yes, this figure shows the same tree, the same length essentially, for with the certain equivalence approximation and the without it, without and with it. The length of this tree is 2L. Okay, it's twice as long because the number of because going from one layer to the next does not involve the W. Because instead of going 2 steps down, it goes 1 step down. So with the certainty equivalence approximation, you get longer look ahead for the same effort. So if your objective is to apply as long look ahead as you can with a given computational budget, this comes in very handy and helps a lot.
Other variants of certainty equivalence approximation, instead of just limiting ourselves to have one stochastic W, then we have 2 or 3 stochastic W's followed by other deterministic W's. Here we just have the first control, and then one W is stochastic, whereas we fix the other ones with nominal values.
Right, yeah.
Can we have other variables?
What about a bunch of random variables? Another random variable.
No, 2 W's would be. Oh, okay.
Yeah. Okay. So that doesn't make sense. Well, what I'm saying is you can aggregate them into a single random variable.
Okay. And it would be the same as this.
Yeah. Oh.
Yeah, these are vector W's. These W's are vectors, right? Okay, they're not necessarily, I call them random variables, but they are really random vectors. They can have multiple components. They're just, WK is a bunch of certain stuff that happens at time K, but it could be more than one number, more than one variable. Okay. Let's go now to Monte Carlo Tree Search. It's a stochastic form of pruning, cutting down on the simulation by pruning unnecessary controls, or what we think are unnecessary. So we have assumed that we evaluate all the Q factors of all the controls at a given state with equal effort, equal number of samples. Let's say we have 10 controls, we're going to apply 1,000 samples for each one. Now, the drawbacks of this is that some controls may be clearly inferior. Some of these 10 controls, let's say 5 of them, you can reject right off the bat on the basis of some preliminary calculation. It may not be worth as much sampling effort, may not be worth to do 1,000 samples on each one of them. Maybe you can do like 10 samples on them and then reject them right off the bat. Also, some controls that appear to be promising, they may be worth exploring better with more samples, just to be sure that we're getting the best one. We can do more sampling and also multi-step look ahead, take advantage of the possibility that the possibility of multi-step look ahead. Now, Monte Carlo Tree Search is geared in that direction, trying to alleviate these drawbacks. Is some form of approximate look-ahead minimization that tries to economize in simulation time, and it involves adaptive simulation. By this, I mean simulation effort adapted to the perceived quality of different controls. And the mechanism with which it works is balancing exploitation and exploration. Aims to balance exploitation, meaning the extra simulation effort on controls that look promising, take advantage of them as much as possible, or evaluate them as best as possible, and exploration, make sure that we don't overlook other controls, we adequately explore the potential of all controls. Now, here's something that some possible source of confusion, because if you read the literature, people tell you that Monte Carlo Tree Search improves performance. Monte Carlo Tree Search does not directly improve performance relative to full-blown multi-step look-ahead. It works like simplified rollout and pruning. It just cuts down the simulation effort, but this savings allows you to look longer, allows longer look-ahead with the same computational budget. That's where the improvement comes from. You don't improve performance, but with less simulation effort, you can look longer, and then you can gain from that. There's a lot of misconceptions about Monte Carlo Tree Search, how it does, how it should be operated, why it's good, when it's good, and so on. It's generally a flaky methodology, but it works for some problems, and with special tuning on the problem at hand, it may work. It may or may not work. That's the bottom line on Monte Carlo Tree Search. Okay, so let me explain Monte Carlo Tree Search for the case of one-step look-ahead, one-step approximation in value space. So what do we do with approximation value space with one-step look-ahead? We look at the current state, we look at all possible controls, and we assume a finite number of them. And then for each one of those controls, we simulate the trajectories forward and calculate the corresponding Q factors, right? Cost of the first stage, cost of the remainder, using some J tilde. Doesn't have to be rollout here with a given policy, just some J tilde. And you have to simulate it. And here's how we do this. We don't take each control in sequence and do zillions of simulation samples on them. Let's take control 1, do 1,000 samples of that, then take control 2, 1,000 samples of that, control 3, 1,000. We don't do it that way. Instead, we pick one control at a time, we pick one sample for that control, and then pick another control judiciously and get the next sample. So here's the scheme. Pick a control in some way, according to some calculations, and generate a single sample of the Q factor. Then go to another control and to another control, depending on the results. Now, after I have collected N samples, I have an empirical mean of the Q factor of every control. However, with a different number of samples. I have, let's say, done 1,000 samples. I may have allocated 500 samples on this control, 200 samples on that control, and 300 samples on that one, right? Because of the sampling policy that I have followed. So at the nth sample, after the nth sample, let's call QUN, the empirical mean of the Q factor of a control U. So this is the mean after N samples. N is the total number of samples that I have. And we view this as the exploitation index. It's a measure of quality of U based on the simulations that I have done so far. And then I could use this estimates to select the next control to sample. But then there arises a problem. Some controls may look good in the beginning and continue to look good and good and good because the other controls are do not look very good. And then I overlook the others. And how do I know that with more simulation, these other controls may not become better? So I want to make sure that I do not overlook some controls that have been less explored with fewer samples. So we simulate some controls a lot, but some controls not enough. We have to get back to those to make sure that indeed they are inferior. So that's where the conflict and the tension comes between exploitation and the exploration. I need exploitation means I sample controls that look the best based on the current sampling results. Exploration makes sure that I explore the potential of all the controls, and I haven't overlooked any without sufficient consideration. So how do we do all this? We balance exploitation and exploration by using an exploitation index and an exploration index. This is the popular strategy and the strategy that's being used in Monte Carlo Tree Search. We introduce an exploration index in addition to the exploitation index. This is the running estimate of the Q factor of that control. And then I calculate also an exploration index that tells me how much I have explored this control. And I add the two, and I sample the one that has the best sum. Now, how do I get this exploration index? I use a confidence interval approach, whereby RUN gives me an estimate of the error that I have in the simulation calculation of that particular control. And the formula for this R is I'm giving it to you here. This particular formula is called the UCB rule, upper confidence bound. And it is, roughly speaking, an estimate of the error bound for the Q for that particular control. And it comes from a different problem, from analysis of a different problem, multi-arm bandit problems, where it has worked very well and it's based on solid theory. And it has been adapted to multi-step look ahead and approximation in value space and Q factor estimation. It has been adapted heuristically speaking, okay? And the formula is something like this. C is a tunable parameter. At time n, here you have, we have collected n samples, right? And we consider a control U. Log n is the number of samples so far. And S of U is the sample count of control U. N is the total number of samples at the present time. SU is the number of samples that have been allocated to control U. And C is a value that, okay, usually between around 1, let's say, square root of 2 is nominal usually given. But in practice, you have to select it by trial and error. And also, this formula assumes that these Qs have been normalized to take values between -1 and 0. All of this works some of the time, okay? With a lot of tuning on the particular problem that you have. Sometimes I've had, from my own experience, it's possible to try for days and days to tune this scheme on a particular problem, and it may not work, okay? On the other hand, it does work sometimes, and in particular, it has worked on alpha 0 with an extension of this rule here to multi-step look ahead. This is for one-step look ahead. But alpha 0 does not use this formula. Use a different formula, again, based on heuristic considerations. We just found it to work well in their training of the, in both in their training and also in the online play. So that's roughly the story on Monte Carlo Tree Search. In your textbook, you're going to see material on this. You're going to see references for multi-step look ahead. It's a subject that has been researched a lot and still being researched. And there's one more thing that I want to mention about Monte Carlo Tree Search. It's geared towards stochastic problems. It doesn't make sense in a deterministic setting. Remember that for deterministic problems, we discussed pruning and multi-step look ahead, and other things like incremental rollout and so on. These schemes make sense on a deterministic setting. Monte Carlo Tree Search does not make sense on a stochastic setting because it's geared towards stochastic simulation. There's no stochastic simulation in a deterministic setting. Still, you'll see a fair amount of literature about extensions of Monte Carlo Tree Search to deterministic problems. Basically, they convert the problem from a deterministic to a stochastic problem for the sake of applying Monte Carlo Tree Search. Okay, it's a little bit of a twisted logic, but you may take a look and judge for yourself. Yes.
Are using next stage, next show, and when does these kind of exploration or exploitation stops? When did you decide to not sample anymore for any shows?
When you reach your simulation budget constraint.
So
let's say, excuse me, you set a certain target number of simulation samples. That's how much you can afford to do, okay? When you reach that point, then you stop and you select whatever control gives you the highest Q, okay?
There's like two kinds of threshold. The first one is with respect to the N. That's one sample, and then after that you do the exploration and exploitation, and then it should be budget stops.
Yeah. You set a goal of, let's say, 10,000 samples, and then one by one you allocate the next where you're going to which control you're going to sample, and you keep a running count of these Q's and R's and select the one that has the best sum.
So you see like two-stage exploration.
I'm sorry, I didn't hear.
It's like a two-stage exploration. So the first stage is drawing out to all controls, and the second one is more effectiveness driven, so that it takes the optimal control to look into.
Well, both of them are updated simultaneously, right? With every sample, you update these R's, because this formula requires you, okay, you replace N by N plus 1 with every new sample. And also you update this SQ depending on what you sample. And also you update the Q of the control that you sample. You keep on, it's an online procedure of selection.
Okay, but I assume it shows like one particular promising control to go much deeper.
The final selection of control is going to be at the end of the sampling process. And then you're going to compare all these exploitation indexes, the Qs, which are the estimates of the Q factors. And you're going to treat these estimates as being true Q factors and pick the control that has the minimal Q factor. So during a simulation, these are updated, and at the end of the simulation, we compare and find the one control that has the minimal Q. Okay, so we'll take a break now for 15 minutes, and then we have two more topics to cover, having to do with infinite state and control spaces. Okay, let's go into infinite spaces problems, infinite control space, infinite state space, and approximation in value space under these conditions. Problems like that are typical of control situations, control theory type of problems. And you remember that I showed this slide earlier. There are two basic types of control problems. One is the regulation problem, to keep the state near the origin, like in this classical inverted pendulum problem, where the control is the force that you apply on the cart back and forth. It takes continuous values, doesn't take a finite number of values, continuous. Also, the state space consists of the angular position and angular velocity of this rod, and both, again, take continuous values. The other major control problem type is path planning, like this car going through, find the path. The state space is the position and the velocity of the car in two-dimensional space. Control has to do with acceleration and direction of the vehicle, and there are constraints, all sorts of things, but all of those are continuous. There may be some discrete, in other contexts, there may be some discrete variables, integer variables, but there's always, in these control problems, there's always a continuous component. So now, what's the difficulty with this? Well, we talked about approximation value space, calculating Q factors for every control and comparing them and picking the control of best Q factor. But here there's an infinite number of Q factors. How are we going to calculate them? So we need a different approach to implement approximation value space. And here's one possibility. Let's suppose that the control space is infinite, and we are at a particular state xk. So the control can take a continuum of values here at the current stage, and also a continuum of values in future stages. And one possibility is to discretize the control space, but then the number of Q factors is excessive. I'm not saying that this cannot be done, or it may not work out in some cases, but it's a problem to contend with. It may be that the number of Q factors is so large that you need that it just becomes computationally very difficult to deal with. Now, another possibility is to accept the continuity, the continuous character of the control space, and look at the forward controls as continuous variables, and use some kind of heuristic that involves optimization, but over a limited number of steps, L-1 optimization. And so the total becomes L-1 plus 1 L-step optimization. So an optimization-based heuristic is merged into the first step minimization to become an L-step minimization at every step. Now, L-step minimizations can be done with when it comes to multistage optimization with continuous state and control spaces, can be done with different techniques, nonlinear programming techniques and optimal control techniques, like quadratic programming, gradient descent, and so on. So you formulate a cost function where the controls are the variables of optimization, and you do this, you use nonlinear programming. This type of formulation also can deal with constraints. state constraints or control constraints. There's also a possibility of a terminal cost function approximation, which has to be given in analytical form. It has to be differentiable also to be able to deal with the requirements of nonlinear programming algorithms and optimal control algorithms. I don't know how much background you have in nonlinear programming. It basically, in its pure form, has to do with minimization of a nonlinear function subject to some constraints. And the optimization is done over vectors. And the vectors here are the U controls. And the kind of methods that you will use here is a very broad class of methods. I've written a book on nonlinear programming. I spent most of my professional life actually working on nonlinear programming. The method that you probably have heard is gradient descent, okay, which we're going to talk about in future lectures, where given a certain a current iterate, you move in the direction of the opposite gradient, a negative gradient, trying to make progress in finding iterates with better values of the cost. Other methods are Newton methods, other methods that are in between gradient descent and Newton methods, a very large variety of nonlinear programming methods for both constrained and unconstrained optimization problems, including quadratic programming and others. These methods have a long record of success, and they can be applied within this context. And in fact, they are the principal methods and the original methods that have been applied in the context of MPC, model predictive control. In model predictive control, very often people use this continuous space optimization methods based on quadratic programming or gradient type or Newton type. These are the methods of choice in model predictive control, as opposed to calculating all values, enumerating, doing simulations, whatever you have, and then finding the control with best Q factor, It's a different approach, same philosophy, multi-step look-ahead minimization, but with different techniques, the techniques of continuous optimization and nonlinear programming in particular. Let me give you an example of a class of problems that arises often in practice. It's multistage linear programming. Oftentimes, resource allocation problems over time are being posed as linear programs, where there is a linear system, xk being the state, uk is the control, and these are vectors, multidimensional vectors. A and B are given matrices, and the objective is to minimize a linear cost over time. So the cost per stage is linear in the state, linear in the control, and these are inner product, okay? CK, XK, these are n-dimensional, multidimensional vectors, and this is the inner product. This is a row vector multiplying a column vector. So it's a standard form of linear programming problem, and it can be solved by linear programming methods, except that it can become very large. If the number of stages is large, and if the dimension of these vectors is fairly large, then you can get with a very large dimensional problem that linear programming codes may have trouble dealing with. However, there's another important case which involves integer constraints in addition to continuous constraints. With integer constraints, it becomes a mixed integer programming problem of large dimension, and it can be very difficult to solve. So people have addressed problems like that with reinforcement learning methods and approximation methods. And here's how this can be done in our context. We can use multi-step look-ahead, truncate the horizon, and use terminal cost function approximation. So instead of looking at the entire problem over n stages, at a given state, we truncate and look forward for a limited number of stages. Even if this problem involves integer constraints, it can be handled because it's lower dimension. It can be handled by current software like Cplex. There's some very efficient integer programming software that are available these days. And for moderate dimensions, they can do very well and online. Moreover, this approach handles readily online replanning. So if some of your constraints change over time, or the cost function, or for some of the A and B matrices, you can incorporate them into your calculations and solve this linear programming problems or integer programming problems online. Generalized to integer constraints, as I was saying, and it is possible to use our earlier methods involving discretization, base heuristics, and so on, but this does not exploit at all the linear programming structure of the problem. So there is an advantage in looking at it as a continuous problem to exploit the linear structure because of the availability of linear programming software and integer programming software. Your textbook has more detail on this type of problem and also references that you can look at. Are there any questions about discontinuous spaces problems? Okay, let's go into our last topic that has to do with stochastic programming. This is a classical problem that I remember was a hot topic when I was a graduate student. It was, at that time, it had received attention in the two-stage case, and it was the kind of stochastic sequential decision-making problem that people would formulate because dynamic programming was too difficult. So people were looking for alternatives to dynamic programming. We're talking about the 60s now, 60s and 70s. And this two-stage problem involves two decisions. Initially, I select one decision, U0, then something random occurs. W, say, there's a disturbance here that takes a finite number of values with given probabilities and gives different outcomes, of course. And then you get a chance to apply a second decision after you get to know the value of W. So control, observe the W that has occurred, and control again. Two decisions, two stages. And after the first control is chosen, the W occurs and takes one of M values with given probabilities. Okay, this is part given in the problem. And once W occurs, then we will know its value, and then we can choose a vector that depends on what we have applied first and what we have observed. So it is a policy, basically, for the second stage. The state here is the state here is the pair of control and disturbance. And here there are four of them, and one of them in the beginning. So there are 5 variables for optimization here. And we want to minimize this expected. This is the cost function, the cost of the first stage, C0, and then the expected value of the cost of the second stage, right? Here are the W's with their probabilities, corresponding probabilities weighted. This is the expected cost of the second stage. So we can write down directly the expected cost in terms of the variables U0 and U1, the 4 variables U1, and this becomes a problem that you can try to optimize using nonlinear programming or linear programming, something like that. Now, what's the difficulty with this formulation? Well, if you have a large number of W's, then the number of U's that you have to consider here is also correspondingly large, okay? And then if you had 3 stages, you could repeat this figure, right? And then the number of possibilities for the 3rd stage would grow exponentially. And as you consider more and more stages, the number of variables U increases to the point where this minimization becomes very difficult. So that was the state of the art for a long time and still is in stochastic programming. 2-stage stochastic programming problems are solvable, but once you go to 3, 4, 5, and so on, you eventually hit a wall very quickly, and you can't solve them. So that brings into play reinforcement learning, which can deal with large dimension. Are there any questions here? Incidentally, there are many problems in the literature that you can find, practical problems that people have formulated and cast in this form. One of them is production planning is a general class of problems where U0 is to decide on the production of resources that you are going to allocate to a certain project. W is the demand for the product that you're going to the demand for the product that's going to occur sometime after you set up the production facility. And then the U's in the 2nd stage are the amounts of product that you're going to allocate for satisfying the demand. So if you don't produce enough here, then there's going to be some deficit if the demand turns out to be high, and there's going to be a penalty associated with that, and so on. I don't want to go into details, but that's one example. There are many other examples of the same type. And you can look at books of stochastic programming to see the range of applications of problems here. Okay. So in multi-stage stochastic programming, the decision is a function of the history up to that point. And we can use a similar formulation as for the 2-stage case, but the exact solution by dynamic programming or nonlinear programming gets rapidly out of hand as the number of stages increases, because the number of variables, number of states that you get after a number of stages increases exponentially. And therefore, the number of variables that you have to consider in a given stage also increases exponentially with the number of stages. So here's how we can address the problem alternatively by reinforcement learning. We can view it as a special case of finite horizon stochastic optimal control. Therefore, approximation in value space applies. Then rollout with or without truncation applies. And one possibility for base heuristic would be 2-stage stochastic programming. Use a 2-stage stochastic programming with some terminal cost approximation as the base heuristic. And this base heuristic is an optimization-based heuristic, but it is of shorter horizon than the full horizon of the multi-stage stochastic programming problem. Moreover, certainty equivalence approximations can be very useful in stochastic programming context. The first W is stochastic. Subsequent disturbances are fixed at nominal values. And that cuts down the number of controls that you have to consider, and it makes the computations much easier. Or you could consider alternatively, instead of certainty equivalence, some form of limited simulation whereby you simplify the probability distribution of W to a fewer possible values, which reduces the number of of states that you can encounter in the future. So all of the stuff that we have been considering in other contexts can be, to a greater or lesser extent, be applied to multi-stage stochastic programming with good chance of success. Your textbook has some references of applications of this type, and you may consult them if you want to see more details and get more understanding. So this is the end of this lecture. Are there any questions? Okay, we're coming into the spring break. After the spring break, the next lecture, at least by our present planning, is to talk about stochastic estimation, Bayesian optimization, adaptive control, and application to the wordle puzzle. There is a lecture, I think it's lecture 9 or lecture 10 I think lecture 9, in last year's offering, and you can look at the slides and the video from that lecture. This material also is in sections 210 and 211 of your textbook. Okay, here's the video lecture, lecture 9. And the other thing I wanted to mention is to remind you that a proposal for your term paper, a summary proposal for your term paper, will be due at the end of the spring break. And in some sense, we're moving into a different phase of the course, where the focus is going to be not on homework or new material, but rather your projects. I expect you also to be involved with that and focus on that, to do an interesting and project that perhaps can interface with your current research, if you're doing research at the moment or looking for the research topics. We want very much to help you. If you need some ideas, you should generate the ideas yourselves. Don't expect us to give you a project, okay? On the other hand, if you need some advice on how to go about your chosen area of concentration, we'll be very happy to do that, all of us. So I wish you rest and have a good spring break.